So in the last module, we introduced memory controller design and discussed three important functions of memory controller design. And now in this module, we will continue with the remaining three important functions. So those are address mapping mechanisms, refresh management techniques, and the memory scheduling. So we know that processor issues load and store requests in terms of physical address to the memory, and but actually the data stored in the memory in terms of the channels, ranks, banks, rows, and so on. Because the physical layout of the memory consists of the set of DRAM devices, part of DIMMs, and logically this entire DRAM memory can be considered as set of rows, set of banks, set of ranks, and set of channels. Effectively, the address mapping is a mechanism which resolves the physical address issued by the processor to the memory in terms of this channel ID, rank ID, bank ID, row ID, and column ID. And why do we have to study these address mapping mechanisms? The address mapping mechanism is a key function in the DRAM memory controller design because it affects the performance significantly. Consider a scenario where if you are going to map the consecutively addressed cache lines to the same row in a bank, then when the first request comes to the DRAM device, we activate the row so that the subsequent requests can get a hit from the open row. So as a result, we can exploit the row buffer locality, and that improves the performance. On the other hand, for example, if you are going to place these consecutive addressed cache lines to two different rows in the same bank, now when we open the first row to service the first request, after servicing that, now when we want to go for the second request, we have to close this because there is a row conflict. So this shows that if the address mapping is not proper, we may incur significant number of conflict misses at the row level, row buffer level, and that degrades the performance. And similarly, so if the address mapping is not proper, it may so happen that all these addresses can go to the different ranks, and when we want to move from one rank to another within a channel, then we need to incur rank to rank switching. So as a result, we have to ensure that proper address mapping mechanism is designed for our memory controller to work efficiently and to improve the overall performance. Not only performance, it also impacts the overall power consumption. So the goal of any address mapping mechanism is to minimize the chances of bank conflicts in temporally adjacent requests and maximize the parallelism in the overall memory system. Once we have a good address mapping which exploits parallelism available at different levels, then the overall performance can be improved. And similarly, once we minimize the bank conflicts for our temporally adjacent requests, so that the performance can be improved. So before discussing the address mapping mechanism, let us see, so what are the granularities at which a parallelism can be available in the memory system. It available at different levels. We know that a DRAM memory system consists of channels, which in turn consists of collection of ranks. Each rank consists of collection of banks, and each bank consists of set of rows, and a row consists of collection of columns. So at the highest level, we have this channels, and so once we map our consecutively addressed blocks to the different channels, then when we want to access these blocks, we can send the request simultaneously to these two channels or whatever the available number of channels, and we can exploit the parallelism significantly. So it means like always the blocks which are consecutive in access, if you are going to distribute that to multiple channels, and all these channels can work independently, and we can improve the performance significantly. So that indicates that when we are coming up with an address mapping, we have to ensure that the channel ID in the address part should be mapped to the lower order bits in the address. The next one is rank. We know that a single channel can cover multiple ranks, and if you are going to distribute or consecutively addressed blocks to multiple ranks, now when we are accessing one rank for a particular cache block and now we want to access the consecutive address block, then we have to go to the other rank, and if you do that, we need to incur a penalty of rank to rank switching, TRTRS, and we discussed in the last module. For a DDR4 system, this rank to rank switching is 2 cycles, and we unnecessarily incur a penalty of 2 cycles if you are distributing our consecutively addressed blocks to multiple ranks. So as a result, we need to keep the consecutively addressed blocks as much as possible to a single rank, so that we don't have to incur this rank to rank switching. And we know that each rank consists of multiple banks. Now all these blocks, all these banks within a rank can work independently. So as a result, what we can do is we can map our consecutively addressed blocks to different banks within a rank. So of course, when we want to access consecutive address blocks, we need to switch between bank to bank, but unlike rank to rank delay, we don't have any bank to bank delay if the banks are within a particular rank. So as a result, we can exploit parallelism by accessing multiple banks that are there inside a single rank, and this parallelization can be exploited as long as we have the shared resources available, the shared resources such as the address bus, command bus, data bus, and so on. So that way we can exploit parallelism at the bank level. And now within a bank, we will have large collection of rows, and now once we have large collection of rows, we can distribute our data. But if you are going to distribute our consecutively addressed cache blocks to different rows in a single bank, then we are going to incur a penalty, because in a bank, even if there are 100 or 200 or thousands of rows, at any point of time we can work with only one row. So when we open a particular row, then we cannot access any other rows in the bank unless we close the previously opened row. So that says that if we map our consecutively addressed cache blocks to different rows within a bank, we incur a significant penalty in terms of row closing and row activation. So we will incur T pre and then T act. On the other hand, if you are going to map our consecutively addressed cache blocks to a single row within a bank, we can exploit the row buffer locality significantly. In such case, we incur only a T cache time to access the data from the open page. So that indicates that we have to map our row ID to the higher order bits in our address. And finally, the columns. Where do we map our columns? The column is going to specify the particular position in our opened row to read the data. So now again, in this, if you are going to use an open page policy, we already discussed page management policies in the last module. An open page policy, a page will be opened until there is a row conflict, and whereas in the case of closed page policy, as soon as we perform a cache, we start issuing a pre, so that we can close this page and we can make the page status to be empty, so that when we want to access the next row, we can start with act command, so that the pre will not be in the critical path. Now when I consider an open page policy, because the open row will be there as it is until there is a conflict. So as a result, if we are considering an open page policy, we have to map our column ID bits towards the lower order bits of our address, and since the lower order bits will change frequently and consecutive blocks can get a hit in the open page. Whereas in the case of closed page policy, because we are going to close immediately after servicing a particular request, so we need to map our column ID bits to the higher order bits of the address. So this way, like, we can exploit our parallelization at different levels, and we need to map our channel ID, rank ID, bank ID, row ID and column ID to appropriate positions in our given address. So now we will consider an example to see how to come up with a decent address mapping mechanism for open page policy and closed page policy. So consider a memory system with k channels, each channel having the L ranks per channel, and each rank has B banks in it, each bank has R rows in it, and each row has C columns, and each column has V bytes in it. Effectively, the overall size of the memory is the product of K, L, B, R, C and V bytes. And we also assume that the K equal to 2 power small k, L is equal to 2 power small l, B equal to 2 power small b, and so on. And effectively, if we have 4 channels in our memory, we require 2 bits of information to code the channel ID. Similarly, for example, if we have 8 banks per rank, then we need 3-bit bank ID and so on. So now once we have the total memory of size k into L into B into R into C into V bytes, we require, so now because typically the data transfer between the multiple levels of caches and the memory happens at the cache line granularity, so we relate these last 2 terms C and V in terms of the cache lines. So for that, let us assume that n be the number of the cache lines per row and G be the bytes per cache line, so that C into V can be replaced by n into Z. So effectively, we have a total memory of size k into L into B into R into n into Z, and this memory can be expressed using k plus L plus B plus R plus n plus Z number of bits, where each of these are the number of bits required to indicate the corresponding the component. So if I consider a baseline and naive address mapping mechanism, I can consider the higher order bits of my address pointing to the channel ID, next few bits are pointing to the rank ID, next few bits are pointing to the bank ID, next few bits are pointing to the row within the bank, next few bits are going to specify the cache line ID within the row, and finally the block offset inside a cache line. So when we consider this naive address mapping, what is going to happen is, because our channel ID is at the higher order bits, as a result all our addresses are confined to one channel, and if the application is requiring more space than the space covered by a channel, then only it will go to the second channel. So that indicates that this address mapping cannot exploit the parallelism at the channel level. And when we are considering, because in this naive address mapping our the channel the cache line ID is mapped to the lower order bits, and if you are using a closed page policy and if the application is accessing subsequent cache lines, so for every subsequent cache line access we incur a penalty in terms of closing the row and then opening the row. So that means in the closed page policy, this naive address mapping may not be efficient, and similarly whether it is a closed page or open page policy, because our channel ID is mapped to the higher order bits, we cannot exploit the parallelization at the channel level. So that's the reason why this naive address mapping mechanism, where the channel ID is at the MSB bits, and whereas the cache line ID is almost to the close to the lower order bits, is not a good idea. We need to come up with efficient mechanisms for different page management policies. And remember, in our page management policies, we consider 3 different techniques. One is an open page policy, the other one is a closed page policy, and the last one is an hybrid policy. And we already discussed that the hybrid policy is efficient in terms of exploiting the access behavior or access rates. So it's effectively, the hybrid policy can dynamically adjust itself based on the access rates of requests coming to the memory, and also looks at the access locality within a rank. So among all these 3 policies, hybrid policy is better. But the same thing cannot be applied in the case of address mapping, and when we stick to one address mapping, we have to stick to that throughout. So as a result, we can give address mappings only for either the open page policy or closed page policy. We cannot give that for a hybrid policy. So when we consider a baseline address mapping mechanism for open page policy, the address mapping looks something like this: R colon L colon B colon N colon K colon Z, where Z is the byte address in a cache line, and K is the channel ID, N is the cache line ID, B is the bank ID, L is the rank ID, and finally R is the row ID. So row is mapped to the MSB. The change in the bit values in the MSB position is much lower compared to the change in the bit values that are at the lower order positions. So as a result, once we map our row ID to the MSB position, so it may not change frequently. As a result, once we open a row, the row can be opened until there is a conflict to that particular row, and we can minimize the row conflicts by mapping our row to the MSB position. And since K is mapped towards the LSB, so we can interleave cache lines across multiple channels. Let us assume that we have 2 channels, and so that the first cache line will be stored in one channel, second cache line is stored in the second channel, and this continues alternatively. And after the channel ID, we get the cache line ID. So as a result, this shows that the consecutive cache lines will go to the subsequent channels, and after the channel ID we have a bank ID. So this says like for the same rank and the same bank, the cache lines belong to a same row can be mapped onto multiple channels, so that when we open a row from a bank of a rank, the row can be opened for significant amount of time to get more and more row hits. And in the case of closed page policy, we know that once a request is serviced, we have to close the page. Now in this case, if you are going to map our adjacent cache lines to the same row, we are going to unnecessarily incur a penalty, because the closed page policy clearly says that once a request is done, the open page needs to be closed. So that indicates that we have to move the column ID towards the MSB side. So when we consider that, we can clearly see that the baseline address mapping for closed page policy is something like this, where R is still at the MSB position as that of the open page addressing mapping, and similarly K is also towards the LSB side as that of open page policy, but the column ID is moved towards the MSB positions, unlike the open page policy where it is towards the LSB side. So this indicates that the columns of a same row should be distributed to multiple channels, but within a channel it should be distributed to different ranks and different banks. But whereas in the case of open page policy, we want to distribute the cache lines to different channels, but within a channel we want to map that the same row, same rank and same bank. So that is the whole difference between open page and the closed page policies, open page and the closed page address mapping schemes. And now we will consider a simple example where we have a memory system consists of 2 channels, and each channel has 2 ranks, and each rank has 2 banks, and each bank has multiple rows. Now we will consider also we consider per row will have 4 cache lines. When we consider 32 consecutive cache lines, and if we consider an open page policy, we can clearly see that the consecutive addressed cache lines are mapped to channel 0 and channel 1. 0 is mapped to channel 0, 1 is mapped to channel 1. Similarly, cache line 2 is mapped to channel 0 and 3 is mapped to channel 1, and so on. And within that, again, for bank 0 of rank 0 of channel 0, if you see, the cache lines 0, 2, 4 and 6 are mapped, and similarly for channel 1, rank 0 and bank 0, we mapped the other 4, that is block number 1, 3, 5 and 7. And similarly we can explain for the other block positions in the address mapping for open page policies. And when we consider the baseline closed page address mapping mechanism, we can clearly see. So if you consider the first 8 blocks, the cache line 0 to cache line 7, cache line 0 is mapped to channel 0, rank 0, bank 0, and cache line 1 is mapped to channel 1, rank 0, bank 0, and cache line 2 is mapped to channel 0, rank 0, bank 1, and the cache line 3 is mapped to channel 1, rank 0, bank 1 and so on. So effectively first 8 blocks, if we consider, these 8 blocks are covering all the channels, all the ranks and all the banks in the case of closed page address mapping mechanism. But whereas in the case of open page policy, the first 8 cache lines are confined only to a single rank. Within that single rank, it is confined to only a single bank, but these blocks are distributed across 2 channels. So that way, like because the objective of the working of open page policy is different from the closed page policy, and the objective of open page policy is different from that of the closed page policy. So when we consider the address mappings also, we need to consider these page management policies and need to come up with efficient address mapping mechanisms by considering the underlying page management policies. So with this, I am concluding this address mapping mechanism, and now we will move on to the refresh mechanisms. We already discussed that the charge in the DRAM cells are going to leak gradually, and we need to refresh these DRAM cells to maintain the data integrity. So as a result, we need to refresh these cells at regular intervals, and once we do this, automatically the corresponding DRAM device cannot be available for servicing any requests from the processors or IO devices. That is going to degrade the performance. So as a result, we need to understand how the refresh mechanism is happening, so that we can know what is the overhead we will get in terms of the overall performance, and then we can think of coming up with an efficient refresh management policies. So we know that the data in the DRAM cells decay based on the temperature on the DRAM device. If the temperature is below 85 degrees centigrade, then the DRAM cell can retain the data for up to 64 milliseconds, but if the temperature is above 85 degrees, then it is going to retain the data only for 32 milliseconds. So within that time interval, we need to refresh the DRAM cell so that it retains the data for next 64 millisecond or 32 millisecond based on the temperature on the DRAM device. So since these refresh operations are interfering with the request from the processor and the IO devices, and the DRAM device is not available during this refresh interval, so that indicates that it is going to have an impact on the bandwidth, and also it is going to consume the power. So as a result, the refresh mechanism is important thing to deal with, and we need to come up with an efficient mechanism to minimize the overheads associated with this bandwidth loss and the power consumption. In order to minimize the impact of the refresh on the bandwidth or the power consumption, or in order to come up with a simple memory controller design, we need to come up with an efficient refresh mechanisms. There are several refresh management techniques proposed in the literature, but we are going to discuss basic refresh management techniques in this module. In order to reduce the complexity associated with the DRAM memory controller design, one simple technique we can do is, we will go for all bank concurrent refresh mechanism. So in this mechanism, the memory controller issues a single refresh command to a DRAM device, and once the refresh command is given to the DRAM device, all the banks inside the DRAM device will undergo for refresh, and they refresh a single row in each of these DRAM banks. Let us assume that if a device has 8 banks, when I issue a refresh command, so from each bank we are going to refresh one row. Though we have not discussed one important timing parameter associated with the DRAM memory controller, that is TFAW, for activation window. This timing parameter is given mainly to ensure that the peak power consumption of this memory system is not crossing a threshold value. This FAW indicates that within an interval we should not activate more than 4 rows. So when a device has 8 DRAM banks, when I issue a refresh command, I cannot refresh one row from all these 8 banks simultaneously. We have to refresh 4 rows from some 4 banks inside this DRAM device and wait for some time, and then refresh the other 4 from the remaining banks. And this is mainly to satisfy the TFAW constraint. Now this is simple, the all bank concurrent refresh mechanism is simple in terms of the memory controller design. The reason is, all we require is only one refresh command, so that once the command is given, the refresh operation is performed. And to implement this, all we require is, we need one register that is called as a refresh address register, which stores the address of the last refreshed row. So whenever the memory controller issues a refresh command, it updates the refresh address register with that row ID, and once that is done, again it looks at the refresh address register content and then increments and then issue the refresh to the subsequent row. Effectively, if you have a DRAM bank consists of 8192 rows, this is a standard. Typically most of the low capacity DRAM devices will have 8192 rows per DRAM bank, and in such a scenario, when I apply this all bank concurrent refresh, first I start with row 0, I refresh it, then go to row 1, refresh it, and go to row 2, and so on. We will continue to the last row of the bank, and because a refresh command is given to all the banks within a device, so finally at the end, once we issue a refresh command to the last row of each of these banks inside a DRAM device, the entire DRAM device is said to be refreshed. But if you do this, it is going to incur significant penalty if processor requests are waiting to be serviced during this interval. We know that each refresh operation consists of reading a row, activating a row, reading the row content to the sense amplifiers, and writing the data from sense amplifiers back to the row. So this we need to perform for each of the rows inside a DRAM bank, and when we have a DRAM bank of 8192 rows, then it is going to take significant amount of time, and that is going to degrade the performance significantly, and especially when there is a performance critical request from the processor is waiting to be serviced by the memory, and if the memory is busy with the refresh, then we are going to incur significant penalty. So though this all bank concurrent refresh is efficient in terms of the design complexity, but it is not efficient from the performance point of view. And the JEDEC standard specifies that in a DRAM device we need to issue a total of 8192 refresh commands, so that for one refresh command we can refresh one row from a bank inside the DRAM device. But now these days we are getting the DRAM DIMMs with higher capacity, higher and higher capacity, and such as, for example, we have a DIMM with 32 gigabits of capacity. So as we want to increase the capacity of DRAM device, we have to increase the number of rows inside a DRAM bank. Once we increase the number of rows, so effectively for each refresh command we have to refresh not just one row but multiple rows from each bank. In other words, for example, if you have a DRAM bank consists of 32k rows, so for each refresh command we have to refresh 4 rows, and that is going to take significant amount of time for each refresh operation. Effectively our TRFC is going to increase because our TRFC is proportional to the number of rows to be refreshed per the refresh command. So as a result we are going to incur a significant penalty. So that means like this all bank concurrent refresh, when we are doing contiguously without any interrupt, without any gap between refreshes, then we are going to incur a penalty significantly. In order to overcome this, we can come up with a different mechanism called as a distributed refresh. This distributed refresh mechanism says that rather than refreshing all the rows inside a bank, so what we can do is we will refresh few number of rows now and then give a gap so that processor requests, if any waiting to be serviced, will be serviced, and then again move on to a refresh, and then again back to the normal mode and then refresh mode. Effectively we interleave or refresh on the normal mode of operations, so that rather than issuing all 8192 refresh commands continuously, we give one refresh command now, wait for some amount of time to service processor or IO requests, and then again go for the second refresh command, and then again wait for some amount of time to service processor or IO requests, and this continues further. And the interval between two refresh commands is called as T refresh interval, T refi, and this is effectively 7.8 microseconds, where we get this value by dividing the 64 millisecond interval with 8192. And if it is an extended temperature mode, then our interval will be 32 milliseconds. So as a result, T refi will be half of this 7.8 microseconds. So the main idea of this distributed refresh is, don't refresh all the rows, don't issue all the refresh commands to a DRAM device continuously. Give a refresh command 1 and then give some space so that the processor request can be serviced, and then again go for a second refresh command and so on. Interleave your refresh and the processor operations simultaneously so that the performance penalty due to refresh can be minimized. So this is about the refresh management, and finally we will move on to the memory scheduling. We already seen from the microarchitecture of memory controller that there are two schedulers. One is for a request scheduler, the other one is a command scheduler. And the request scheduler is actually taking the requests from the request queues, and we consider two request queues, one for storing read requests from the processor and IO devices, and the other one is to store the write request. So in the case of request scheduling, the scheduler can pick one read request and then go to a write request and then go to a read request and so on. it can interleave between read and write. But if we do so, we unnecessarily incur a penalty, because as we discussed in the last module, whenever we are moving from write operation to a read operation, we need to release the IO gating resources held by the previous write operation, so that the subsequent read operation can perform its operation successfully. In order to do that, we will incur a penalty of 4 cycles, that is T write to read delay. So as a result, it is not a good idea to select requests between the read queue, write queue in alternate cycles. We have to consider a different mechanism wherein typically we continuously get the request, select the request from a particular queue, maybe from the read queue, and service the request to a certain point where the number of requests in the write queue is crossing a higher danger mark. If it is crossing a higher danger mark, that indicates that the write queue is sooner going to be full, and then we have to stall everything and then drain the request from the write queue. That is going to degrade the performance significantly, and as a result, whenever the number of entries in the write queue is going to cross a danger limit, higher danger limit, then we will move on to the writes, and then we will pick the request from the write queue. So while we are picking the request from the write queue, then the request in the read queue will keep on increasing, because the processor or IO device can send requests, and this is going to go up. And while we are servicing the request from the write queue, after some time the number of requests in the write queue will go to a lower value. So it is like once it crosses the lower threshold, then immediately we will move on to the read queue and select the request. So that again it takes some more time for write queue to fill in its entries, and then we will service the read request from the read queue. So whenever we are performing operations, or whenever we are selecting requests from a read queue, then we call it as a read major mode, and if you are going to select the request from the write queue, then we are going to call it as write major mode. Similarly, like the lower and the upper thresholds for write queue, we also have the lower and upper threshold for the read queue. Once these thresholds are reached, then automatically we are going to move on to the other queue and then select the request continuously from that particular thing. So with that, like we are going to select a request from a read queue or write queue based on whether it is a read major mode or a write major mode, and once we select a request, now we will convert that request into memory commands. By the way, when we are selecting a request from a read queue or from a write queue, our request scheduler can reorder the request. So as a result, our request scheduler can select requests in out of order fashion. It need not follow the same order in which the processor initiated the request and so on, because we know that the requests to the request queues, read queue or write queue, can come from different agents. The requests may be from a display agent, requests may be from a GPU graphic agent, requests may be from the CPU agents, or within even CPU agent also, it may be from different applications. So we can reorder these requests based on the application criticality or based on the application importance or the agent importance. So the request scheduler will do these reorderings and select a particular request from a particular queue based on it's a read major mode or a write major mode, and then the selected request will be converted into set of memory commands. And once the request is selected and converted into set of memory commands, and these memory commands will be stored in a bank wise command queues. We already discussed in the previous module that, so we have a collection of command queues which are at a bank granularity. So each bank will have one queue. Of course, it is not a queue effectively, because we perform the operations in the FIFO order. Of course, the advanced memory controller designs will go for different orderings within the bank, but if you are going to do this out of ordering of request selection from the command selection from the command queues, then so we have to insert pre, act and cache for each of the requests. But if you are going to go for a FIFO ordering in the command queues, then context aware conversion of a request to the commands can be applicable. So in the last module we already discussed, like if there is the second request to the same row as that of the previous request, then I can issue only one command, that is a cache, to the corresponding command queue. But if I am going to go for an out of order execution at the out of order selection at the command queues at bank level, then for each request we have to pick up 3 commands, pre, act and cache, and based on the context at the state of the row buffer at that particular position, we can discard some of the commands. But that is going to make the overall design complex, and we are not going to consider that in our module. So to make the memory controller design simple, we will consider our command queues work in FIFO order, the order in which the commands are inserted into the command queues. And these command queues are going to work at the bank level, and once we insert some set of commands to a particular bank level command queue, and the requests in that queue will be processed in the order in which they are inserted. The first request will go first and the second request will go second. And once we have the requests converted into commands and the commands are stored in bank level command queues, now there is a command scheduler, and the role of the command scheduler is to select one particular command queue from the available lot of the command queues. And for that it can go for different policies. One may be a simple round robin policy. This is mainly to ensure the fairness among multiple the banks. So just go for a bank 0, go to the bank 0 command queue, next bank 1 command queue, bank 2, 3 and so on, and come back to the bank 0 within a rank, and similarly it can select across the ranks and the channels. This is a simple design, round robin, but it may not give you performance improvement significantly. And similarly there is another policy which is a first ready first serve. Whenever we want to select a request, whenever we want to select a command, we can just look at all the first entries in all the command queues, and whichever is ready, among all the ready commands we will see which one is issued first, so that we can take care of the age into consideration, so that some agents may not be starved to service its request and so on. So this is again like you can improve performance as well as fairness can be improved here. And similarly you can also consider other age based policies in selecting a particular the command queue among all the available command queues by using this command scheduler. So with that we will complete this the memory hierarchies design. And in summary, in the 2 weeks of lectures we considered the cache memory design, the internal organization of a cache memory, and several optimizations that can be performed on cache memories to improve performance, minimize energy consumption. And we also discussed the microarchitecture of the memory controller. We discussed the basics of DRAM based memory, and what are the issues involved in designing, what are the functionalities of memory controller, and we discussed page management policies, address mapping mechanisms, refresh mechanisms. And in order to come up with efficient memory hierarchy design, we need to come up with efficient cache replacement policies which may be adapted to the application behaviors, and at the same time it should not incur significant overhead. And also from the memory DRAM based memory point of view, we need to come up with an efficient address mapping mechanisms, efficient page management policies, as well as efficient memory scheduling policies. And those who are interested in understanding more about the functioning of DRAM based memory, they can look at DRAM Sim, which is a publicly available DRAM simulator from University of Maryland, and you can download this and then you can simulate DRAM based memory, and you can see the impact of different address mapping mechanisms, or you can see for the different configurations of the memory increasing the channels, increasing the ranks, or considering a different address mapping mechanisms, or applying the refresh management techniques, and several other things you can play with the simulator. So with that, I am concluding this memory hierarchy design. Thank you.